In this lecture, we will introduce a somewhat more sophisticated idea than conditional probability, that is, conditional expectation. To begin, as a reminder, if we have a given probability space with an event A of strictly positive probability, then we can form the new conditional probability measure P sub A, which is defined like this, which represents the new posterior probability of events after we know that event A has occurred. Now, one thing we can do is to just take that as our new probability measure and take the expectation with respect to it. We might call that expectation sub A, and we can also call it expectation given A, like this. We just integrate our random variable with respect to the new probability measure PA, if the random variable is in L1 of that probability measure. Well, in fact, given that the event B had positive probability, L1 of the new probability measure is the same as L1 of the old probability measure, and we can quickly compute that this conditioned expectation is just the expectation of X and A divided by the probability of A. Now remember this notation here. Expectation of X colon A means the expectation of X times the indicator function of the event A. To prove this, foreshadowing the way a lot of proofs are going to go in the next few lectures, we will start with a simple random variable X. So it has finite range, and I've written it therefore as a sum of some values, alpha j in the reals or complex numbers, times indicator functions of some disjoint events, bj. Then by definition, the integral of x against the measure pa is the sum over j of alpha j times pa of the event bj. By definition of conditional probability, that's the sum over j of alpha j times the probability p of a intersect bj divided by the probability of a. And now, if we simply factor out that common factor of pa, we can recognize this as 1 over pa times the integral of the sum over j of alpha j times the indicator of bj intersect a integrated against the original measure p. And notice that this sum inside is the sum over j of alpha j indicator of bj times the indicator of a, since a product of two indicators is the indicator of their intersection. But that's just the original random variable x there, and so this becomes the expected value of x times the indicator of a divided by the probability of a, as claimed. So we've proved the lemma for simple functions. Now for any sequence of functions, we can approximate it by simple functions. Perhaps the simplest way to approach things here is that for general x, let's say real valued, we can write it as x plus minus x minus. We can now find a sequence xn plus of simple functions that converges to x plus from below, and a sequence xn minus that converges to x minus from below. And that means that xn plus plus xn minus, which is the absolute value of xn plus minus xn minus, since both of those are positive valued, is less than or equal to x plus plus x minus, which is the absolute value of x. Our assumption was that x is L1, so this is our uniform dominating L1 function, and therefore, since we have pointwise convergence of these and therefore this, and therefore by the dominated convergence theorem, xn plus minus xn minus integrated against pa converges to the integral of x against pa. But we just finished showing that since those are simple functions, this is the integral of xn plus indicator of a dp minus integral of xn minus indicator of a dp, all divided by the probability of a. And by a similar dominated convergence theorem argument, we can show that the left-hand side here converges to the expected value of x and a divided by the probability of a, concluding the proof in general. Now that's expectation with respect to the conditional probability measure, but that's not what conditional expectation is. Conditional expectation is a new random variable. And to understand where that comes from, we're going to now, for the rest of this lecture, consider the situation that is sometimes presented in undergraduate probability courses, where we have a partition of our sample space into a finite or countable will be fine collection of positive probability events. We can then take the expectation against the conditional probability measure of any one of those, but we can also string those all together into a single function. That is, with respect to that fixed partition, we can consider the conditional expectation given the partition of any L1 random variable. Remember, L1 with respect to any of these conditional probability measures is the same as just L1 of the original prior probability measure. And we'll define that as follows. It's the sum over the partition indices of the expectation given the partition event an times the indicator of the event an. In other words, this is a new random variable which on an outcome omega takes the value, expected value onto an of x, provided that omega is in an. Since the an's form a partition of our probability space, each omega is in exactly one an. And so this is well defined. It's also a linear combination of indicator functions of events, and so it is a measurable function. It is a random variable. Now we're going to do something now that might seem counterintuitive and in fact not well defined. Instead of labeling this random variable by the particular partition, we're going to label it by the sigma field generated by that partition. We're going to call it conditional expectation onto this sigma field G, E sub G. Why can we do that? And why should we do that? Well, why we can do that is the following exercise, which is on your homework. Given a countable partition of the sample space into events, they don't even need to be positive probability for this statement to make sense. The sigma field generated by that partition is nothing other than the collection of all, at most countable, unions of events from the partition itself. That is, the partition blocks are atoms for this sigma field. The sigma field is generated by them, and every event in the sigma field is a union of those pieces. That means that in principle we can recover the original partition from the sigma field G, because it is the minimal generating set. So therefore, it's at least well defined to label this thing by G instead of by the particular partition. Now the bigger question is, why would we want to do that? So one brief answer is the following immediate corollary, which is that if we fix a partition an and let G be the sigma field that it generates, then this new random variable, the conditional expectation of x onto G, is G measurable. Now, that just follows from the fact that this is a linear combination of indicator functions of events an, and those an's are in G because G is the sigma field that they generate. In fact, since G is the sigma field generated by the partition pieces an, we see that the minimal sigma field with respect to which the conditional expectation onto G of x is measurable is, in fact, G. And so it does make sense to label it by G. Now, all that being said, it's only really possible to actually recover the partition from G if you have a finite partition and therefore a finite sigma field. Then it's relatively easy to pick off. Otherwise, we have a collection of countable unions of things, which is an uncountable set. G will certainly be uncountable in that case. In fact, it's a good exercise that every sigma field is either finite or uncountable. So we can't exactly write down a list of the elements of the sigma field and then start taking intersections in order to whittle down to a generating set. We'd really like to have a better, more invariant definition and understanding of what this conditional expectation random variable is, even in this partition setting. We're going to head towards that shortly. But first, I'd like to give one motivating example to understand where this is going to come up over and over in the coming lectures. Suppose that we have a random variable defined on our probability space, taking values in some countable state space S. Now in this case, when I say taking values, I mean that we're imposing the constraint that for each S, the probability that y is equal to S is strictly positive. Otherwise, we just wouldn't include that S in the state space. Now, since y is a function, of course, the set of preimages of all of the points in the state space forms a partition of omega. And so we can talk about conditional expectation with respect to that partition or with respect to the sigma field generated by that partition. Alternatively, well, what's the sigma field generated by that partition? By definition, it's the minimal sigma field with respect to which the random variable y is measurable. And so if I have any random variable x that is L1 with respect to the original sigma field, the conditional expectation of x onto this partition is the conditional expectation of x onto the sigma field generated by y, which we will frequently just write as the conditional expectation of x given the random variable y. Just be careful, that always means this. We're always taking conditional expectation with respect to a sigma field. Now, from our definition so far of what conditional expectation means, this is the sum over the indices of the partition of conditional expectation onto each of the events in the partition of x times the indicator of that event occurring. And of course, integrating with respect to that conditional probability measure, that means we're taking this sum here. In other words, for each outcome, omega, the conditional expectation of x given y at omega is equal to the expected value of x times the indicator of the event that y happens to take the value y of omega, divided by the probability of the event that y takes the value y of omega. Now, one thing that is clear from that formulation is that the value of this random variable doesn't really depend on omega. It only depends on y of omega. This should really be thought of as a function not of the original sample space, omega, but of the state space of the random variable y. But we didn't need to write this out to see that that would be true, because, as we showed on the last slide, this conditional expectation is measurable with respect to this sigma field. But the Doob-Dinkin representation tells us that the set of measurable functions with respect to that sigma field is exactly the set of Borel functions composed with the random variable y. And so we knew already that this conditional expectation was equal to g of y for some real-valued random variable on the state space S. Now let me show you some notation which is going to confuse matters more, but it's good to get it under your belt early. That function of the state space is often written as the conditional expectation of x given that y equals s. Now this lines up with our earlier notation, as we can see right from here. In fact, since y equals s is a positive probability event, this has a well-defined meaning as the expectation with respect to the conditional probability measure conditioned on the event y equals s of the random variable x, which is exactly what this is right here, and we see that we do get agreement there. However, it's important to note as we move forward soon into the territory where we'll be conditioning on events that have zero probability, that this same argument holds true. If we can condition on this sigma field here, the resulting random variable is going to be some function of the random variable y. And we will still refer to that function of the state space like this, even though this literally doesn't make sense if this event doesn't have positive probability. So now let's start to move towards a more invariant way to represent this conditional expectation so that we can extend beyond the case of a countable partition of positive probability events. And here is the key result that's going to make that work. If we're in the context where we have a countable partition of positive probability events, and G is the sigma field generated by that partition, then if I take an L2 random variable of the original sigma field and an L2 random variable that is measurable with respect to this sigma field, then I can compute the L2 inner product, expected value of xy of those two, by first conditioning x on G. X was not G measurable before. What we do is we condition it so that it is G measurable, and the resulting expected value of that product is the same as the original. Now, hidden in here is the statement that the right-hand side makes sense, which means that this had better be an L2 random variable, or else this product may not be integrable. That's going to come out in the wash of this proof. In order to prove this result, we're going to take the same approach we did earlier. We're going to start by working with simple random variables and then generalize using the approximation tools from measure theory that we know and love. So we'll start with the case that y is a simple random variable. That means that we can write it in this form. And the bj's are going to be in this sigma field G because y is a G measurable random variable. Now notice there's no need anywhere in this proof for this to be actually simple. It can take countably many values just as well as finitely many. That will be important in the sequel, so let's go ahead and assume that this may as well be a countable sum. Now, as you're showing on your homework, since bj is in G, and G is the sigma field consisting of all countable unions of elements from A, we can write each bj as such a disjoint union over some countable collection of indices of the AKs, the original partition sets. And that means, since we're allowing y to have countably many values as it is, we may as well write y instead as the sum of some coefficients, beta k prime, times the indicator of AK, where beta k prime is equal to beta j for all j for which k is in lambda j. Now that means, by dominated convergence, if you'd like to work out the details, that the expected value of xy is the sum over k of beta k prime times the expected value of x times the indicator of AK. Now on the other hand, if we calculate the conditional expectation of x given G, that's, by our definition so far, equal to this sum here. And that means that if we combine these two sums, we get that the expected value of the conditional expectation of x given G times y is the sum over j and k of the expected value conditioned on aj of x times beta k prime times the expected value of the indicator of aj times the indicator of ak. But the product of two indicators is the indicator of the intersection, and the AKs were a partition, so they are disjoint. That means that this thing here has expectation equal to delta jk times the expected value of, say, indicator of AK. But that's the same thing as delta jk times the probability of AK. And so we can write this double sum as just a single sum of terms that survive, sum k going from 1 up to infinity of the expected value conditioned on ak of x times beta k prime times the probability of ak. But the expected value conditioned on ak is just defined to be the expected value of x times the indicator of ak divided by the probability of ak. And so multiplying through by that again means that the term inside here is just beta k prime times the expected value of x times the indicator of ak And that means we've exactly matched up to here and shown that these two are equal in this setting, where y is a potentially countably valued simple function. So now we'd like to extend this proof to the case where y is not necessarily countably valued. It's just any old L2 function measurable with respect to g. But of course, we're going to do what we did before and approximate such a y by simple functions. We know that we can do that. And in fact, as we showed in an earlier proof in this lecture, we can do it with g-measurable simple functions that are uniformly bounded by the function y. Since y is in L2, that means all of these ones will be in L2 as well, and will have a uniform dominating L2 bound. Now, since yn converges almost surely to y, that means that x times yn converges almost surely to x times y, and the x times yn by this will be uniformly bounded by x times y. Since x and y are both L2, by the Cauchy-Schwarz inequality, their product is in L1, and so here we have a uniform dominating L1 function. That means that we're set up for the dominated convergence theorem, and so the expected value of x times yn converges to the expected value of x times y, one of the two sides of the equation we're hoping to prove in general. But we just finished showing in step 1, since these yns are simple functions that are g-measurable, that we can replace this expected value by conditioning x on g first. And so to conclude the proof, we would love to show that this converges to the expected value of the conditional expectation of x onto g times y, which will show that these are equal as we'd like. A similar dominated convergence theorem approach will work here, but in order to apply it, we need to see, and certainly need to see for this to even make sense, that this random variable, conditional expectation of x onto g, is L2. If so, then we can use this as a uniform dominating function for these ones and apply the dominated convergence theorem. So to see that in this simple context with a partition defining our conditional expectation, we can just compute. The L2 norm squared of the conditional expectation is the expected value of the square of this sum. Following exactly the same calculations we did on the last slide, using the disjointness of the events aj, this, which when you square it will become a double sum, will have a bunch of terms that have probability 0. And so it will in fact expand as a single sum of expectation given aj of x quantity squared times the expected value of the indicator of aj, which is just the probability of aj. Now let's look at this quantity here. By definition, that's the expected value of x times the indicator of aj divided by the probability of aj. Now we're going to estimate this term using the Cauchy-Schwarz inequality. The expectation of x indicator of aj will write as the expectation of x indicator of aj times the indicator of aj, utilizing the fact that the indicator function of a set squares to itself. Well, Cauchy-Schwarz inequality therefore tells us that the square of that expectation is less than or equal to the expected value of x indicator of aj squared times the expected value of indicator of aj squared. But the indicator of aj squared is itself, and so this is just the expected value of x squared times the indicator of aj times the expected value of the indicator of aj, which is just the probability of aj. And so this term here is less than or equal to the expected value of x squared times the indicator of aj times the probability of aj divided by the probability of aj squared. And so we just have a single probability of aj down there. But now that's going to cancel with this term here, and so altogether we get that this sum is bounded by the sum of the expected value of x squared times the indicator of aj. And now we can bring that sum inside the expected value. The sum of the indicator of aj is just the constant function 1, because the aj's form a partition of the probability space. And so this sum is just equal to the expected value of x squared, or the L2 norm of x squared. Thus, what we've shown is that the conditional expectation of x given g is an L2 random variable, and in fact its L2 norm is less than or equal to the L2 norm of the original random variable x. And that means that we can redo the dominated convergence theorem argument that we used above almost word for word. We take the conditional expectation of x onto g times yn. That's less than or equal to the conditional expectation onto g of x times y. This is a fixed L1 function because this is L2, as is this by assumption in the question. And we also have, of course, since yn converges almost surely to y, that this integrand converges almost surely to this. And therefore, by the dominated convergence theorem, we do indeed get this convergence, which shows the equality of these two in the generality that we wanted to prove. And that concludes the proof. Now you may have noticed that a lot of the arguments in this proof, both steps, required some L2 orthogonality type considerations, and that's no accident. In fact, this result is the key to understanding what conditional expectation really is. We need a definition that doesn't rely on the existence of a countable partition of the probability space so that we can take conditional expectations onto more general subsigma fields. And the way to do that is precisely to define the conditional expectation to be the unique thing that satisfies this equality. At least in the L2 context, that uniqueness will follow from the fact that, as we'll see, conditional expectation is really just orthogonal projection.